We are now going to look at Liouville's theorem, which was originally proved by Cauchy. Liouville's theorem says that the only bounded entire functions are constants. Let's just take a moment to appreciate this theorem. So this fails miserably for R. If we were working in real analysis, and sine, cosine, for example, are bounded. They don't exceed 1 in size, but are non-constant, of course. So bounded, so also sort of differentiable on all of R. So they're entire, if there is a word for that for R. But they're certainly non-constant. Okay, so what Liouville's theorem is saying is that in C, if you have an analytic function on all of C, so that's it. This is analytic on all of C, differentiable on all of C, that is bounded, then it must be constant, which is pretty wild. So here's our thought bubble. Let's put that to the side. Let's prove Liouville's theorem. The proof is not going to be difficult. Since f is bounded, the modulus of f is less than or equal to m for some m. Okay. No matter what value we plug in, it will not exceed m in modulus. By Cauchy's inequality, the size of the derivative's value at any point is therefore less than or equal to 1 factorial m over r for any circle of radius r about z naught. So that's just m over r. And this is where we're going to use the fact that f is entire. So first of all, the derivative exists. That's fine. But it actually, f is defined on all of C, and the derivative exists on all of C. So since f is defined on all of C, we can make r as big as we want. That is, if we apply sort of the limit as r goes to infinity of both sides, well, the left-hand side has no r's in it. It's just the modulus of the derivative, so it's just that. But the right-hand side goes to 0 as r goes to infinity. And so what this is telling us then, that the value of our derivative at any point is 0 for all z naught in C. But we saw that when the value of the derivative is 0, f is sort of independent of z. And so in particular, f of z is a constant. And that's it. That's what we want to show.